A to 2 plus A to 1. Y'all with me on this, everybody? That's just standard, right? In our case, A to 1 is air, correct? So it's A to 9. So we know A to 1 is A to 9. Now, A to 2 is copper, right? Copper has a conductivity of 5.8 times 10 to the 7th, 1 over ohm meters or Siemens. Y'all follow me on this, class? It's a very good conductor, y'all agree, by any measure. So we come here, and now what we need to do is get A to 2 for copper. And we're going to do that by first identifying certain things. First, does everybody see omega is 2 pi times 10 to the 8th in this one, class? Y'all with me? So it's 2 pi times 10 to the 8th, and that's radians per second. And now we come down and get eta. Well, for copper, A to 2. Square root, technically it's J omega mu over sigma plus J omega epsilon, right? And how am I going to modify that? Probably, I don't have to. Anybody? Let me ask you this. Sigma is 5.8 times 10 to the 7th, right? Omega is 2 pi times 10 to the 8th, and epsilon for copper is just epsilon naught, right? So this is almost non-existent. Do y'all agree? If you want to put it in, go ahead. It's not going to matter. But this is about equal to what? It's about equal to the square root of omega mu over sigma at an angle of 45 degrees, or e to the j pi over 4. Now, why did I say, y'all agree I can get rid of this, right? And the square root of j is really e to the j pi over 4, 45 degrees. Do y'all agree? Everybody, give me a show of hands if you got me on this one. All right? So now we need this value. What's this going to be? It's going to be the square root of 2 pi times 10 to the 8th, right? Times mu naught, which is times 4 pi times 10 to the minus 7, over sigma, which is 5.8 times 10 to the 7. So this is, and it's going to be at that angle 45 degrees, e to the j pi over 4. So what is this stuff going to be? So I got, what is that going to be? Pi comes outside. I got a small number here, really small. Anybody? Like 10 to the minus 3 or 10 to the minus 4? Can somebody give that to me? Y'all follow me what I'm doing here? Just calculating the intrinsic impedance of copper. If you can give that to me, that'd be great. I just need the magnitude.
Yeah.
Which you got?
3.69 times 10 to the minus 3.
That sounds about right. E to the j pi over 4 ohms. Okay, now calculate this. I want you to take a look at this before you just brute force it. I've got A to 2 minus A to 1. A to 2 is of the order of 10 to the minus 3. A to 1 is 120 pi, or 377, right? You see how this really is going to be about minus 1. We can put it in there if you want to do the math on this, but we can put in the 3.69 times 10 to the minus 3rd e to the j pi over 4. It's not going to matter. Minus 120 pi, or minus 377, and divided by the sum. But what are you going to see this becomes? This is almost ridiculous to do. Just by looking, what can you see that is? It's minus 1, isn't it? I mean, it may not be exactly minus 1, but if it isn't close to minus 1, there ain't no close. It's about minus 1. Right, which means the entire electric field, about all the electric field that hits there is reflected. Do y'all follow me? So that means if we want an actual equation for the reflected field, it's about equal to that, with one caveat. It'll be minus, right? Y'all follow me on that? So if we put this incident field in a phasor form, let me do it that way. E phasor would be 10, right? E to the minus j beta 1, we'll get that in a second, z in the AX direction. Now, because E reflected is going to be the reflection coefficient times E naught incident times E to the plus j beta 1 z AX. The reflection coefficient is -1, and y'all see that E naught here, E naught incident, is just 10, right? It's the magnitude of the incoming field. Can y'all read this? I'll make it bigger if you need me to. Can y'all see it in the back? Okay. So here, the reflected wave is just going to be -10, and it's going to be E to the j beta 1 z AX. Now, that's not exactly true completely, but it's so close, who cares? I mean, we're talking about something that may be minus 0.99999 something, all right? But it's about that. Y'all follow me? Now, next thing I want to ask is, how do I get beta 1? Well, what is beta in air? Isn't it omega times square root of mu epsilon, right? And what's the square root of mu epsilon in there? Square root of mu naught epsilon naught is 1 over c, isn't it, class? Isn't it? I mean, y'all follow me? So this is really equal to omega divided by the speed of light, or it's 2 pi times 10 to the 8th over c, which is 3 times 10 to the 8th, and that's 2 pi over 3 radians per meter. Right? So that would be beta 1, right? What did they ask for exactly in this problem? Help me out. We got the reflected field. Now we can put it in the time domain if you want, but I don't know what domain I want. That's the phasor domain.
And the time average power density transmitted at the surface.
Okay, now we can get that, but he's talking about into the surface. Do y'all follow me? So here, we're going to get the transmission coefficient. Does he ask for the E field reflected or not?
Yes, he does.
Yes,
Is it the phasor or time domain?
It's like time to
Time movement.
All right, if we want it in the time domain, how would we do it? That's the phasor domain, right? What do we do if we want time?
plug it in.
It's going to be take that times e to the j omega t and take the real part, correct? That's the technical way of doing it. But from the past, you know, really what's going to happen is you're going to take that magnitude -10, right? And then it's going to be cosine of omega t. The omega is 2 pi times 10 to the 8th t. Right? Minus or plus, now it's plus beta 1. Beta 1, which is 2 pi over 3 times z in the AX direction. That would be the reflected E field in the time domain. And now if we want the transmitted power, I want you to pay attention to this part. I hope that's what he has. All right? But for the transmission coefficient, remember, tau is a transmission coefficient. It's equal to 1 plus the reflection coefficient. Well, if you just take the approximation, it's 0, right? So what we actually do is use the formula. It's 2 times a to 2 over a to 2 plus a to 1. That is the transmission coefficient. It's 2 times the impedance you're going into over the impedance you're going into plus the impedance you came from. That's always it. Now, here's how that approximation works. When a to 2 is so much smaller, take a look at this and make sure you see it. You see how you have a to 2, super small, 10 to the minus 3 kind of stuff, right? Plus something that's about 377. So what we do is just get rid of that. And we say the transmission coefficient is about that. That means the transmission coefficient is about 2 times a to 2, or times this, 3.69 times 10 to the minus 3 times e to the j pi over 4. We won't even need that, over 120 pi. So you can give me that number, magnitude, and then just leave the e to the j pi over 4 there. It's going to be small. It's going to be what? 10 to the minus 6, I think, something like that, 10 to the minus 5?
19.6 times 10 to the negative 6.
10.6?
19.6.
19.6. And it's e to the j pi over 4, right? I want to make sure you all see this. So that's the transmission coefficient. That means the did you get something different?
No, I got Sanders.
Okay. That means that the transmitted electric field into the copper, just on the other side of that boundary, would be, and I'll put it here. If you want the phasor form of it, it would be what? E transmitted would be transmission coefficient times E naught incident, right? And then it would be times e to the minus alpha z, e to the minus j beta 2z in the AX direction. Do you all follow me on that? Transmission coefficient times E naught incident is the magnitude of the transmitted electric field, right? If you wanted the formal equation, we could get gamma and beta by what? I mean, alpha and beta, pardon me, which would be the same because it's a very good conductor. We could say gamma is equal to the square root of j omega mu times sigma plus j omega epsilon in the copper, right? Y'all follow me on that? Now, what approximation would I do here? The omega epsilon is so small compared to sigma, right? Copper sigma is 5.8 times 10 to the 7. I just erased that for a good conductor. And that means that I would get gamma is equal to alpha plus j beta, and it would be simply 1 plus j times the square root of pi f mu sigma. Now, I've done a couple of things here. First, I know that omega is 2 pi f, okay? And I know when I get square root of j, what I end up with is 1 plus j over the square root of 2. And if I mess with it a little, I get this. Do you all remember me doing that? How many do? Okay. Now, just for completeness, what is this value going to be? F is, do I have F here? I don't have F. By looking, what is F? Take a look. 10 to the 8th, right? And that's hertz. So if that's 10 to the 8th, can you punch the numbers on this one and just tell me what it is? And I'll leave it as 1 plus j times something. Just square root of pi times 10 to the 8th times mu naught, which is 4 pi times 10 to the 7 times 5.8 times 10 to the 7. I'm just curious myself. And alpha will be beta, right? It's a good conductor. So y'all follow me on that? Alpha and beta will be the same.
151.
We'll say again?
151 times 10 to the 3.
Times 10 to the 3rd? Okay. 151 times 10 to the 3rd radians per second, or really what? Napiers, or radians per meter, or Napiers per meter. Y'all follow me? That would be alpha and beta. What do you notice about the size of this compared to beta in the first one? Beta here is what? 2 pi over 3, right? It's about what? Well, it's about 2, a little over 2, right? Look at this. This is what? It's 1.51 times 10 to the 5th. It's 5 or 6 orders of magnitude larger. Do y'all follow me on that, class? Much, much, much bigger. Means that the wave, that the actual number of wavelengths, or I should say, the number of changes, or the wavelength itself, is extremely small in the actual copper. All right, I'm just pointing this out. So you could use this for alpha and beta if you wanted an equation for it. Do y'all follow me? I'm doing this for a reason, because this, on a final exam, this information I may want from you. So I want to make sure you know how to get it. Now, I come back here. The real question was about power, just the amount of power that's transferred in per square meter, right? So if we have this, looking for a space, I'll do it here. So this would be in the copper. We see that the actual E field that's transmitted in the copper would be transmission coefficient times E naught incident. And we know it's E to the J pi over 4, but that doesn't matter. So just take this times 10. Do you all agree the incident field's 10? That just changes it by what? Makes it 10 to the minus 5th. So this is going to be 19.6 times 10 to the minus 5th E to the J pi over 4 volts per meter. We don't care about the rest of that. Y'all with me? Now the power, this is one thing you have to understand. Power formula, if you have a good conductor, you have to do this. The average power, this is for a normally incident wave, is going to be 1/2 times the magnitude of the transmitted field, which is E naught incident times the transmission coefficient squared, over magnitude of eta. I guess I erased eta, but that's that 3.69 times 10 to the minus 3, right? Then there's also what? There's a cosine of the angle associated with eta, which is 45 degrees. Do y'all follow me on that? So I'll put cosine of pi over 4 here. And if you wanted to have the variation with depth, there would be an e to the minus 2 alpha z, and this would be in the AZ direction. The reason the 2 is there is because it's power. It's going to attenuate twice as fast as the electric field. Y'all with me? That would be a general equation. At z equals 0, we can just get rid of this, and we could say the average power now, we can put the numbers in. It'd be 1/2 times 1.96, or 19.6 times 10 to the minus 5th squared over eta, you correct me if I'm wrong, 3.69 times 10 to the minus 3. Is that right? Is that right for eta?
Yeah.
And then times the cosine of pi over 4. Well, that's 1 over square root of 2. So I might as well leave it as 1 over square root of 2. And that would be the average power in watts per meter squared penetrating into the steel. What is that value? It's going to be small. I don't know how small, but pretty small.
3.7 microwatts.
3.7 microwatts. And that'd be watts per meter squared. Is that the answer? Okay, that's how you do that problem. But I want to tell you, the thing is, the orders of magnitude of difference in the actual values of the intrinsic impedance need to be considered carefully, because here, if you do 1 plus the reflection coefficient, well, the reflection coefficient is about -1, you get 0, right? So you have to use the other form of that, which is 2 times eta 2 over eta 2 plus eta 1. You can ignore eta 2 in the bottom. That's the way it's done. Okay. That's a good problem, because it's a conductor, and most people, if there are mistakes made, it's usually calculating the transmission coefficient is 1 plus the reflection, and they'll assume it's 0, and that's not correct. There is some that actually gets in there and does heat the surface of the copper, or it penetrates into the copper. Any other question? That's a good question. I like that. Nothing? All right, I got a question for you. So over here, I got the instant electric field, right? What would the power density be, the incoming power density? Just look at this. What's power, we're in a lossless region, if it's, right? What would it be? 1/2, right? Magnitude of the E field squared over eta. I'm just asking general questions, right? What is it for the reflected field in that region? Same exact formula, only now it would be 1/2 reflection coefficient times incident field squared over eta, right? So if you just take the incoming power density and multiply it by the square of the reflection coefficient, you get the reflected power density. Y'all hear me on that one, class? Something to keep in mind. Now, the truth is that's not quite true, because what? I mean, that would be the power density flowing in the reverse direction, because I approximated the reflection coefficient as -1, exactly, right? in truth, it's slightly less than this. How much less? Well, if you calculate the power density that's into the region, that's actually transmitted into the copper, subtract that from the power density of the incident wave, then you will get the reflected power density exactly. Y'all follow me? So just be aware of these things. These are slight things that may have a major effect on some answers, okay? I'm just telling you that. One other question for the crowd. We've talked about power density. We have an expression for the electric field. How would we get an expression first for the magnetic field in the copper? And then how would you get the velocity and wavelength in the copper? So if we're in the copper, we're in the transmitted region. I'm going to erase this. Think about it now. These are all kinds of questions that I'll ask you on the final exam. I'm trying to prepare you. All right, think about it. How would I get the H field that's transmitted? Well, it's a plane wave, right? It's propagating. If I wanted the H field, I could say it's 1 over eta, right? And then direction of propagation crossed into the E field if I was in the phase of the main. Do you all agree with that? That'll work. That'll work every time. And I'll probably ask something like this. Hint, I will probably ask something like this. All right? Put a big underscore. Baginski said, it's coming at us. All right? Know how to do this. All right? So let's just go through this. I'm trying to be fair about this because I say stuff sometimes and I think people, oh, who cares? He's not going to ask that. Am I going to ask? I am going to ask this. All right? So now back to this thing. H transmit is 1 over eta, right? Eta is some super small number, which is what? 3.69 times 10 to the minus 3, but it's e to the what? J pi over 4. You got to add the angle there. With me? Then it's going to be unit vector in the direction of propagation is AZ, correct? I'm doing it in the phasor domain first. And then it's crossed into the E field. Now, I've got to put this in a phasor form. Y'all follow me? That's not phasor form yet, is it? What's the phasor form? That's this guy over here, isn't it? Y'all follow me? That's the transmitted field, right? So transmission coefficient times that. Y'all see where I'm going with this class? Then it's times this stuff. And I'm going to leave it. Are you with me on this one? Okay, so what is that transmit field? I'll do it like this. It's transmission coefficient times this, and that's this right here. So it's 19.6 times 10 to the minus 5th, and it's going to be e to the j pi over 4, and then we're going to have e to the minus alpha z times e to the minus j beta, and this is beta 2 times z in the AX direction. Now, I put the whole thing there to make sure you see what's going on. You with me? Y'all with me on this one? Okay. So, I didn't put the alpha and beta in here, but I want to just show you something. You see this? You with me on that, class? Those cancel, don't they? All right. Then when I come here, I have AZ crossed into AX is what? AZ crossed into AX is AY. Very good. So now I have, whatever this is, 19.6 times 10 to the minus 5th over 3.69 times 10 to the minus 3rd. And what else? Then I have E, I'm just going to leave it as e to the minus alpha z e to the minus j beta 2 times z, and this is going to be in the AY direction. And then this would be the magnitude of H. Y'all follow me? What's the magnitude of H there? I don't know. I'm just asking. 51.
53 times 1 times 10 to the minus 3.
So this is 53.7, did you say?
1.
0.1 times 10 to the minus 3. And then it would be times e to the minus alpha z, e to the minus j, beta 2z in the ay direction, right? That would be amps per meter here. And that would be in the phasor domain, right? Now, the E field in the phasor domain, I didn't put the complete statement here, but if I wanted to, I would have to do what? I would have to put e to the minus alpha z times e to the minus j beta 2z here, and it would be ax. Do y'all follow me? To make it also with the distance variation, right? Now please watch this. When you look at these two, this and this, you'll see one thing that's apparent. All right, they both vary the same way spatially, right? They both have the exponential decay and the same beta, correct? But this has a 45-degree phase difference. Do y'all follow me on that? Right? And the truth is, we'll put it in the time domain in a second, when you're in a very good conductor, the E field and H field maximums will be off by 45 degrees in time. They will be skewed. Now, you know how if you have a circuit, if you have just an inductor in it, current and voltage are out of phase by 90 degrees, right? When you have just the capacitor, current and voltage are out of phase by 90 degrees, correct? When you have an inductor and a resistor with the same impedance in a circuit, then the overall voltage compared to the overall current will be off by exactly 45 degrees. Do y'all follow me on that? By 45. Do you know what I'm talking about here? I'm trying to draw an analogy here. So that means if I go to the time domain for the E field here, remember if I want the time domain for the transmitted E field, it'll have the same magnitude, right? It'll be 19.6 times 10 to the minus 5th, right? Then I can put the e to the minus alpha z here. That's a real number. But now I have this phase angle, right? I want to get it into this thing so I can get a beta in here. So it would be, if I wanted that, I'd have to rewrite this as this. Just bear with me. This should be as 19.6 times 10 to the minus 5th times e to the minus alpha z, and then it would be e to the minus j quantity beta z, right? And then it would be minus pi over 4. Can you all see that? Because I got a minus in front of the j, now I have a minus in front of that pi over 4, so when they're multiplied together, it's effectively a positive number. Y'all follow me? And the reason I did this is, when I know I take this, and I multiply it by e to the j omega t and take the real part, then this is going to be replacing just beta z, that last part. So I get this. I get cosine of omega t, I'm just going to leave it as omega t, minus that beta z, beta 2z, and then it's going to be minus pi over 4, or really plus pi over 4 here. And that would be AX. Do y'all follow me on that? And when I did that, now that would be the electric field that would be inside the conductor, and it would be out of phase with, I didn't put the time domain form, but if I wanted the time domain form of this one, do you all see it's going to be just 53.1 times 10 to the minus 3, e to the minus alpha z, and then it would just be cosine omega t minus beta 2z. Y'all see that? I'll write it down for you anyway. So it would be 5.31 times 10 to the minus 3, e to the minus alpha z. This is the time domain. Here it would be just cosine of omega t minus beta 2z a1. And exactly a 45 degrees difference in the phases of those two. That's important though. All right. Now, y'all follow me. That's how you get the H field, the phasor and time domain from the E field that you have. Now, next, I ask for the velocity, phase velocity in the good conductor. How do you get that? How many remember the fundamental definition of phase velocity? Omega over beta, right? It always will be. So it's omega over beta. and beta 2. So omega is 2 pi times 10 to the 8th. What about beta 2? 151 times 10 to the 3, is that right? What's that value? I don't know. It ain't the speed of light, I'll tell you that. Meters per second compared to 3 times 10 to the 8 meters per second. This is something that's doable, right? With the orbital satellites, sure. That's a reasonable one. So what happens is that conductor has slowed the speed of propagation in the conductor orders and orders of magnitude, right? The phase velocity. Now I asked you for one other thing, wavelength in the conductor, into copper. Now what is wavelength fundamentally? Always think about 2 pi, right? 2 pi divided by beta, right? So tell me now what the wavelength is. 2 pi over beta, which is 151 times 10 to the 3rd. This is going to be a shorty. So 0.2 times 10 to the minus 6. Okay.
42.
What?
42.
42. Meters, right? That's wavelength. It's 42 microns. In space, where is that in the visible spectrum? I'm not even sure if that's visible, actually. But you all see what's happening there. The wavelength in free space is going to be much, 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 much longer, right? But that's how you get all the parameters. I want to make sure you see it. Get E, H, get the power, get wavelength, get velocity, so you have completely characterized propagation in both medias, okay? With me? All right. Other questions? I'm trying to make sure I cover everything here as best I can. All right, we're not going to cover oblique incidence by any chance. The last thing we covered is normal incidence.
To do an oblique incidence problem, you just apply boundary conditions to something like this. Is that
What's that?
the basic approach for something like that, though, would be to apply boundary conditions?
That's
to
right,
something
but
like this, right?
there's 2 modes. There are things called TE and TM polarization. Let me just mention this, then I'll continue. So what normal incidence is if I have a wave coming straight down in the stage, and the stage is the barrier between 2 regions, that's normal incidence. It's oblique incidence would be a wave, this is the electric field coming in and hitting the stage at a non-normal angle. That's oblique incidence. But now the electric field can have 2 possible polarizations. It can be like this, or it can be in the plane it hits, all right? Because E and H would be perpendicular. Y'all follow me on that? Oblique incidence has a different reflection coefficient depending if it's TE. Transverse electric means the electric field is perpendicular, or it's parallel really to the planes that it hits. And then there's parallel polarization. This isn't going to make a lot of sense, which is really just rotating the electric field by 90 degrees. There's 2 types. Usually it's called TE or TM polarizations, transverse electric or transverse magnetic polarizations, and the reflection coefficients are quite different. How many have heard of Brewster's angle? What does Brewster's angle tell you? It's the angle of complete transmission, all right? You know what polarized sunglasses are? Has anybody ever taken a pair of polarized sunglasses and put the lenses over each other and rotated them by 90 degrees? You get an absolute dark spot, nothing will penetrate. That's how you know they're polarized. Well, what a polarized sunglasses have are very thin slits in them. And the thin slits will short out any field in this direction, but they'll allow the field in this direction to penetrate the slits. This is basically what how polarization works. And they penetrate, and the reason they do is that it basically uses the concept of Brewster's angle to get all the, quote, glare reflected that can't penetrate. But that'll come later. I'm just mentioning that. I've got 10 more minutes to cover things. I wanted to cover, like on the quiz on Friday that's coming up, remember, if you have done all your quizzes, then this quiz, if you score well, will replace your lowest quiz score. Y'all follow me? And if you missed a quiz, that quiz will be used to replace the quiz you missed, okay? That's my deal with you. The quiz on Friday will cover the last couple of homeworks, all right? That are basically on reflection and, you know, of normal incidents. And I'm not gonna ask you anything about polarization, right hand or left hand. I may be on the final, but I'll be square about it. And on Friday, I'll give you a review for the final. So go through it. If you have questions, please come with questions. If you haven't, we've covered a lot. We've covered transmission lines, right? Smith charts usage to analyze transmission lines. We should probably do one of those on Friday because it's been a while. So if you got a special problem, let me know. You're going to get stub matching, right? I'm just going to say this. You're either going to get shunt or series stub matching, not on Friday, but I mean on the final. Then you have electrostatics, everything. We've done everything from the D field. We've used Gauss's law. We've talked about capacitance and how to analyze situations to get the capacitance. We've talked about resistance, how to figure out the resistance between any kind of concentric shapes. Then we've moved into magnetics, and we've done everything with magnetostatics. We talked about really Ampere's law, how to get the H field from symmetric current distributions. We talked about the boundary conditions too. E tan 1 is E tan 2, H tan 1 is H tan 2 if there's no surface currents. We talked about the inductance, how you get inductance based on either internal inductance or external in some cases, but we've talked about those. We've talked about induced EMF, right? Talked about transformer action, and we've also talked about, I'm not going to ask anything about magnetic lifting forces here, so you don't have to worry about that on the final. But we talked about force on both a charge and on a wire segment. Remember my little story about the buried railroad tracks that supposedly were pulled together. That's the way you know. The current in the same direction pulls the wires together, and opposite direction repels them. We talked about magnetic energy density, electric energy density, and power dissipation. Remember that 2 lectures ago? I put them all on the board at the same time. And now we talked about polarization and then reflection. So those are the sort of the major topical areas in a nutshell. You can watch the recording if you didn't write it all down. And anybody got a problem they want to see? I can pull one out of my hat, but anything at all from any of the chapters we've covered. You got one in mind?
Not really.
Well, capacitance problems usually take the shape of either 2 parallel plates with some stuff in between them, 2 concentric cylinders with some stuff in them, or 2 spheres with some stuff filling them. And you're always going to, you have to make an assumption that either the voltage or the charge is known, and then work to get the unknown, and then saying capacitance is really equal to Q over V. So, got one? Want to come up with one? I'll be happy to. But you got one from mine?
We come up with one that'd be good, just to see something.
What's that?
Come up with one just to see something different, leave the problems in the book.
All right.
Come up with one.
Well, here's one for you. Remember, I did give you you had to be able to identify things that are in parallel, things that are in series. You remember that? So I'm gonna leave that one alone, but now I'm gonna just come up with one. This is gonna be a sphere. We could do a cylinder, but sphere is it's a little different. All right, so now I have a sphere, got an inner radius A, outer radius B, And it's filled with the material with epsilon relative equal to 1 over r, where r is the radial distance. So that's the relative permittivity. Now, I could make it 1 over r squared, I could make it sine of r, but I could make it any kind of function of r as long as that is not a function of theta and phi. If it's a function of angle, then there's no way you can do this problem easily. It becomes a much more difficult problem. But this is something where it's spherically symmetric. So you got an inner conductor and an outer conductor. You can ground that. And I want to know the effective capacitance between the inner and outer conductor. That's what I'm up to. So how do you want to do it? Let's see who remembers. With capacitance, we either assume voltage or charge. Which ones do you want? That would be harder. Charge. Put a charge on the inside, right? Put a charge Q. So we're going to assume Q. Now, after you get that, we're going to put a charge Q here. Y'all follow me? What's the next step? Some of you remember. Well, now I put my Gaussian surface around here, and I know the integral of d dot ds is charge enclosed. Y'all remember that? So from that, I get my D field. And the D field will be Q over 4 pi r squared in the AR direction. Has to be. You'll notice it's not a function of epsilon. That's the beauty of this. But the E field is, right? And how do I get the E field from that? Divide by epsilon, right? Sure, divide by epsilon. So now to get the E field, I got it's Q over 4 pi r squared. Then it's times epsilon r, which is 1 over r. And then it's times epsilon naught, right? Don't forget the epsilon naught. Y'all follow me on that? And that would be in the AR direction. Now, before I continue, how can I simplify? Just look. You see the 1 over r and the r squared multiplied together just result in r, right? Remember, that could be any function of r. It doesn't have to be a 1 over r, or 1 over r squared, or r to the 5th or anything. It could be any function. Now that I have that, what's my next step? Some of you know by now.
Integrate E to find voltage.
I want to find the voltage between the inner and outer conductor, and I only care about the magnitude. Y'all follow me on that? Don't worry about the sign. So I'm going to get the voltage by saying it's the integral of E dot dl from the inner A to the outer B, but really it's the magnitude of that. So now I have integral of Q over 4 pi epsilon naught r, AR, dot, and this would be dr, AR, and it would go from A to B, and that is going to be Q over 4 pi epsilon naught times the natural log of B over A. Do y'all agree with that? Then finally I get capacitance. And remember, with capacitance, really you say that Q is equal to capacitance times voltage difference across the plates. Q is CV, so to get capacitance, I take Q and I divide it by the V I calculated. Y'all follow me? The Q must cancel. So when I calculate capacitance as Q over V, I get that Q just goes away, and I'm left with 1 over 4 pi epsilon naught times the natural log of B over A, or really 4 pi times epsilon naught over the natural log of B over A. And that would be the capacitance, and it would be in farads. Now that's how you do that problem in a nutshell. Some of you remember this. Right? I can change epsilon relative at will. I could make it 1 over r squared, or I could make it r, or I could make it the sine of pi r, or anything like that. Y'all follow me? But whatever I do to that, the only place it changes it is right here And that affects the change right here. And that's it. I almost feel like doing this. I don't think I have time. Let me just ask you this. Same basic geometry. Let's forget about capacitance. I want the resistance between these two. If sigma now is equal to R, all right, just R itself, all right, between the inner and outer conductor. Y'all follow me? For resistance, what did we have to do? Similar, right? But we had to assume something. What did we assume usually? I, right? We're going to assume the total I flowing from the inner conductor to the outer conductor, right? How does it get to the inner conductor? Some very small holes drilled and connected, some wires, insulated wires connected to it, and we ignore the effect of that small hole. That's the idea behind it. All right, so I assume I, what next, guys?
Get J.
Right, very good. And what would J be? You're exactly right. I over the surface area of a sphere, which is 4 pi r squared in the AR direction, right? This is very similar, right? Almost identical. Instead of Q, we have I. Instead of D, we have J. Now, what's my next step? So I know that J is sigma E, and I need E, right? So E is J divided by sigma, and looky there, I get I over 4 pi r squared divided by sigma, and I made sigma r, right? So it's times r. Y'all follow me? So I'll just make that an r cubed if you don't mind. Y'all with me on that? I made this a simple one. R cubed, but I'm going to tell you people mess up this next step. All right, so now I've got E. What do I need next? V, right? So now I've got to integrate E dot dl from A to B, strict positive. I don't care if it comes out negative or not. And that means I integrate this, which is I over 4 pi r cubed AR dot dr AR. And it goes from A to B. This is going to end up being negative, but don't worry about it. So I get AR dot AR is 1, right? Then I integrate, I'm going to take out the constants. I have I over 4 pi. And what is 1 over r cubed? That's like integrating r to the minus 3, right? So it's 1 over 1 minus 3, or really minus 1/2. Do y'all follow me on that? So it's going to be minus 1/2, right? And then it's going to be times 1 over r squared, evaluated from A to B. Now the reason I'm mentioning this is a lot of people mess up the 1 over r cubed integrals. They'll have a 1 over r squared, but they'll forget it breaks out a minus 1/2 in front of it. I'm just warning you on this one. I see it all the time in my classes. Now I don't care if it's negative, do I? But one thing I can do is switch the limits, right? And if I switch the limits, what do I see happening? I have I over 8 pi, right? And then it's going to be 1 over a squared minus 1 over b squared. And that's equal to my V. Finally, how do I get my resistance?
E equals like that. So
I divided, it's V over I, right?
you divided by I.
Right, so I have to take that V and divide it by I. You'll notice the nicety here, right? And that's the resistance. Y'all follow me on that? I just divided the voltage by current. The current was in there, so I get simply that. Y'all follow me? So that would be the resistance. And obviously you can see there's all sorts of problems I can come up with by just changing the radial variation in epsilon or sigma. And remember, that pretty much, I mean, it works for inductance calculations through magnetic energy. So all those things are based on this kind of work. Okay. Finally, I'm over by 4 minutes. I owe you something. I'll figure it out. I don't know what I'll do. I forgot something. If you got other questions, just let me know. We have my office a little bit. Nothing? No. All right. By the way, it's a good, now Friday's the official name, but pretty much it's over now. This is a pretty good class overall, I know. We didn't have any real problems with COVID. Did any of your classes have problems with